Thank you for the introduction. I'm Xinwei, and I'm a PhD student in University of California, Berkeley, and I'm also serving as a research assistant at Lawrence Berkeley National Lab. So thank you for joining me. Today's topic is a case study on zero net energy home called Honda Smart Home in California. A quick introduction. So I guess we all work in the built environment research field, and we all know that one of the biggest challenges we're facing is that with lack of publicly available data with high resolution and high quality. So the Department of DOE, the Department of Energy in the United States has initiated this benchmark data set project to provide a publicly available data set with high high quality and high resolution. And Honda Smart Home is one of the 12 data sets the Lawrence Berkeley Lab is preparing. So we are in Shanghai. And the Honda Smart Home is actually located in almost the other side of the earth, Northern California, which is 1 hour drive from San Francisco. So the Honda Smart Home serves as a student residential housing for the University of California, Davis. Zoom into it, so this is the UC Davis campus and the Honda Smart Home located in the residential community for the university. Davis is actually classified as a hot, dry climate, meaning we have super low participation in summer and will be much humid in the winter. The ample solar radiation provides us a big potential for the PV panel generation. Though in the summer, the weather can be a little bit unendurable, but again, it provides sufficient daylighting for the PV, clean energy. And look at the building itself. It's a 2-story single-family residence with a detached garage and a visitor center. We didn't include the visitor center in our analysis because that's not usual for a residential family. What's intriguing is that it has a HMI system, so the home energy management system, which can log in the data set for over 300 data sensors for both climate and energy use. It also has a bidirectional electric vehicle that can both charge from the house and feed in the house back. Furthermore, it has a demand response management so that it can integrate this house to the local grid. So a quick overview that we break down those 300 sensors into several categories, and we only focus on the energy consumption part of the sensors. We use the year of 2019 as our analyzed year because that's a typical year pre-pandemic. So hopefully it has a continuous application implementation for the future use. And in 2019, the Honda Smart Home is actually 1/3 of the median regarding the energy use intensity with similar, compared with similar housing in similar climate. So I'll be introducing analysis on zero net energy, flexibility, self-sufficiency, and demand response operations and grid resilience. So not to mention the zero net energy is a percentage of the PV coverage, so how much PV generation can supplement the energy consumption. However, when this is defined, the electric vehicle is not that popular among the, within the families. So we are trying to analyze whether including the EV in the future years will affect the zero net energy analysis. So for all the figures, we provide you the ZNE analysis with EV and without EV. So because it as the energy consumption, the ZNE performance can be dropping a little, but actually this doesn't affect the ZNE performance that much. For example, the Honda Smart Home reaches the ZNE goal in a yearly resolution ever since 2018, but if we include the EV, it will just push 2 years later to meet the ZNE goal in 2018. again, we focus on the year of 2019, and if we look at monthly resolution, there will be 9 months from March to November that can meet the Zhejiang goal pretty easily, but it struggles a little bit in the winter months, in January, February, and December. Primarily due to the confliction between the increasing heating demand and the dropping solar radiation. The same tendency happens again in the daily resolution, so we can say it meets the Zhejiang goal in summer and fall almost 100%. However, it struggles a little bit in spring and winter when we don't have sufficient energy consumption. Don't have sufficient solar radiation. Zoom into some typical months. So for example, in May, we have so much ample solar radiation that the PV panels can even generate 5 times of the energy consumption in the building. However, in winter months, again, it's less promising because we still use the energy a lot. However, but the solar radiation drops and fails to meet the energy demand. So for the flexibility and self-sufficiency, we choose 3 metrics to evaluate it. So the flexibility factor is a metric that measures the power usage between the high peak demand and low peak demand. So the high peak hour is defined as 4 p.m. to 9 p.m. in California, and if the flexibility factor is positive, meaning we are doing a great job, we didn't use power during the peak area, which is great. It saves money and it reduces carbon emission. So though it fluctuates a lot, but the 75% quantile of the flexibility factor is 0.2 to 0.8, indicating a good flexibility for our house. And also for the consumption, self-sufficiency, it measures the capability of the PV panels. So we can say in summer, the PV panel can generate more energy than the households needed, so we can feed the excessive energy to the grid to relieve the pressure. And self-sufficiency just reflects the electricity consumption of the household, and it can almost reach 100 self-sufficiency during 10 months within a year. And for the DR operation, we have several strategies. Because the on-site solar energy is converted to the direct current, so it's ideal for charging the EV, which is also operate on direct current. And if the EV is not charging, it will just use the surplus energy to feed the battery for later use. So the strategy mainly is prioritizing using the grid power to meet the households, because we are using the AC instead of DC. And if there excessive energy, like if there are DR demand from the grid, then we feed excessive energy back to the grid during peak hours, 4 p.m. to 9 p.m. And we can efficiently charge in the EV during the low load period, which is time other than 4 to 9 p.m. So here's a detailed case study on January, like two strategies happening. So the first thing is that, so the gray area is where we have the DR demand, and we can see in the left figures that we have a pretty intense energy use. So when we receive the DR demand, we'll just decreasing the energy use from the grid by feeding the house using both battery and the electric vehicle. And if we are maybe not just present in the house, and the energy use is not intense, and the battery is available, then we'll be using the battery to feed the grid. However, as we can see, the battery is not utilized that much. So I think it's used less than 40% in November and less than 20% in other months. With that battery, which is a 10 kilowatt battery, we actually can be grid independent for 10 hours in May and 5 hours in December. However, remember this, we didn't prioritize grid independency in such cases. If we want to really test on the grid independency, meaning, for example, we facing an extreme condition and there's a power outage, which happens pretty frequently in California, then we can probably using the battery fully to charge in the house. So assume that we fully utilize the battery for the household energy consumption, then we can achieve almost 8.6 days, more than a week in summer months. In winter, we still struggles because, again, we don't have enough solar radiation, but it's pretty promising in summer. And one other good thing is that we also got a bidirectional charging EV, meaning we can use the EV to recharge the house. So this vehicle is equipped with 20 kilowatt of battery. So adding the electric vehicle and the stationary battery, we can have 30 kilowatt of battery available to fill the house. With that, we can achieve almost 200 days under extreme condition. Again, this is a pretty aggressive hypothesis, but I guess it shows some potential how the house will be grid independence in extreme weather conditions. So a quick summary that the GNE goal can be met consistently on annual basis, but we have some seasonal fluctuations which poses challenges how to reduce the discrepancy between the solar radiation with energy consumption. And the substantial residential resilience potential during the grid disruptions, thanks for the battery and bidirectional EV. And we can sort of come to the conclusion that the prevalence of EV in homes tend to have limited impact on the zero net energy performance, and it can also serve as an emergency power storage in extreme conditions, aiding the grid independence. So we can be grid independent with 10 kilowatt of battery for 8.6 days, and with 30 kilowatt battery, we can be grid independent for over 200 days. And again, we can use the parked EV as a buffer for the electrical grid, and we still require management and advancement in battery technology. Some of our future work, so I think it can be divided into 3 parts. The energy consumption discrepancy will be again addressed for the discrepancy between the solar radiation versus energy consumption. And we also need careful management for distributed energy resources, and we need an enhanced demand response effectiveness. It can be, our work still missing some important factors identified previously, such as occupant behavior and climate impact. So we're aiming to include those into the modeling process. And also we can do this kind of data set can provide price and policy sensitivity information, such as examine responses to dynamic grid pricing and net metering, and explore ideal PV and battery sizes for future use. So thank you, and I'd like to answer any questions you have.
Thanks Xinwei for her significant contributions. I think for me it's a very interesting results in terms of this net zero energy home. I believe you must have many questions regarding the control strategies and some other regulation methods in this house. So it's time to raise your questions. Okay. All right. So girl first, right? Lady first.
Thank you for the presentation. It's a very interesting house. I saw in your one of your slides in the HAMS, like the sensor, for the energy, like the platform something. You have a couple of different sensors is monitoring some subcategory of the energy consumption. But in your analysis, I didn't see you analyze the data in this session. I'm wondering, in your study related to this house, whether you will do something like related to how different category is consume energy or electricity.
Thank you for your comment. I think you made a good point. So we definitely have multiple categories for data set, and we actually did analysis on that. So due to the time limit, I didn't push too much, push too much slides on that, but we break down the energy consumption by category, by categorical data, and maybe you can read the full detail from our paper. We also will continue to do the categorical data analysis in the future.
Yeah, sure. Thank you. It's a very interesting project.
Thank you.
Thank you for your presentation. I had one question. You listed export to the grid and charging of EV batteries as two measures for dealing with excessive energy production from solar panels. I'm wondering, have you talked about any other measures, such as, for example, sharing electricity with neighbor buildings, or instead of selling back to the grids, do you have these kind of measures also?
If I understand you correctly, our house is kind of experimental on its own, so it doesn't really communicate with its neighborhood building. However, the whole community for the UC campus, UC Davis campus, have installed several PV panels, even on the parking shading system. So I guess it has some neighborhood level interaction within the grid, but our building is currently standalone. But I guess we have a huge potential in integrating the house with the local grid. So that's a great direction for us to continue. Thank you.
Thank you.
Okay, any more questions?
Well, thanks for your presentation. I have a question. Do you consider the degradation of battery and the embodying energy of the vehicle's battery? Because when you use the battery as energy storage, it will reduce the battery's life. And we should consider the embodied energy when calculate their energy.
Well, I think you made a good point that we do introduce the buffer when we calculate the battery potential, so we don't fully use the battery to like 0% POV or charge it to, I guess we charge it to 100%. But I do agree with you that we need to keep it in mind to prolong the battery's lifespan by using it carefully with battery management and control. So that's definitely one of our biggest direction right now, but it's, currently we are just make some aggressive hypothesis and provide the potential with the battery usage. Does that answer your question?
Yes, thanks for answer.
Thank you.
Okay, well then.